Yeah, welcome you all to the Spark Research YouTube channel. This is Dr. Vivchandra, Assistant Professor in the Department of ECE. And currently we are running in this series signal processing. And in this session, we are going to take the contents, particularly from this unit second. And this is the first part of this unit second, analysis of continuous time, signals, and system. So before going ahead, let me tell you, we will come with all the 5 minutes content, and along with that, we will also look into the questions and answers which has asked in the previous semester, as well as we will take the some questions which has asked in the previous gate examinations, right? So here is the syllabus for this second unit, and in this unit, uh, in this session, we are going to take the contents from these topics: Fourier transform, inverse Fourier transform, properties, and the analysis of LTI CT system using Fourier transform, frequency response, and then impulse response and step response. We'll see, right? So let's start. First of all, the first question is that what is the meaning of this Fourier transform, right? So first thing is that suppose there is some signals which contains the multiple frequencies. So it's very difficult to analyze in the time domain. So that is why the important is to convert into the frequency domain, right? So this is the same signals, this one in the frequency domain. So in frequency domain, it is very easy to analyze, right? And again, this is in the time domain and this is in the frequency domain. So primary objective of this Fourier transform is to convert the signal from time domain to frequency domain. Now question is that how will do? So answer is multiply by this exponential function e to the power minus j omega t and integrate it over minus infinity to infinity with the particular function that you want to convert from from time to frequency. That's all, right? Similarly, the inverse Fourier transform means if you wanted to come back from frequency domain to time domain, then you have to multiply by the plus this exponential of j omega t. So this is the primary objective. So let's take some more details. Say the frequency Fourier transform is a mathematical tool that converts a time domain signal into the frequency domain, right? And how will you convert? So this is the f of t that you want to convert from time to frequency, and this is the exponential that you have to multiply in order to convert, right? Exponential of minus j omega t and dt, and integrate it over minus infinity to infinity, and finally f of w you will get that will convert it into the frequency domain, right? And what is this? F of omega is frequency domain representation of f of t, and omega is the angular frequency, and exponential function represents the complex exponential functions, right? That is sinusoidal. As for example, suppose we want to convert this time domain, that is cos omega t, into the frequency. How can we do it? So f of omega, first of all, formula we can write. This is your function that you want to convert, and this is the multiplication factor. That is, we have to multiply by e to the power minus j omega t and integrate it over minus infinity to infinity. Now, how will integrate this? So this is the one challenge. So in order to integrate it, first we will break this cosine function into this exponential. So use the Euler's formula. Cos theta is equal to half of e to the power theta plus e to the power minus theta. So we'll break into this, and then we will multiply with this exponential function, and then we'll convert back in the after the integration. So finally your functions will be pi of del of omega minus twice pi f naught and plus del of omega plus twice by f naught. So this is the process, right? So just put the function that you want to convert, multiply by this exponential function, and integrate it over minus infinity to infinity. So this is the steps, right? Thing is, here are the tables. So the del t can be the what Fourier transform of del t is 1, and then Fourier transform of a step function, that is ut is pi of del omega, then Fourier transform of this rt, that is t into ut is 1 minus j omega square, and then cosine function, sinusoidal rectangular function can be written in the t in the sinc function omega t by 2s pi, right? So these are the Fourier transform of these functions, right? So you can try to find out by yourself. Now, inverse Fourier transform. What is this inverse Fourier transform? So the main purpose, the objective is to convert back from frequency domain to time domain. So this is your f of omega in the frequency domain, and this is f of t in the time domain. So how will convert back this f of omega into f of t? So again multiply by e to the power plus j omega t, right? So here it is plus j omega t, and if you are converting time to frequency, then minus j omega t, right? So plus j omega t and the d omega, and integrate it over minus infinity to infinity and divide by twice by 1 by twice by this is the time period, right? So you will get back into the time domain. As for example, here are the some examples of the inverse Fourier transform. So of course the same, the del t, that is 1 and 1 into del t, right? So inverse Fourier transform of 1 is del t, and then inverse Fourier transform of 1 by j omega is ut. Inverse transform of 1 by omega square is your rt, and then inverse transform of this function is cosine, already we got, right? So in the Fourier transform of this will be this, and inverse of transform will be this into this, right? So vice versa for all. Okay, so example is here, like suppose f of omega is equal to rectangular function omega by twice pi. Rectangular function means it is 1 for less than equal to pi and 0 otherwise. So how can we convert back? So f of omega, then we have to multiply by e to the power j omega t and integrate it over minus infinity to infinity and 1 by twice pi, right? So f of omega is nothing, it's a 1 in between plus minus pi, right? So 1 into this and then integrate it over minus pi to pi, you will get this sine function, right? So you can convert using the Euler's formula, you will get this sine pi by t by pi by t. So this is sine function, clear? Similarly, you can get the inverse Fourier transform of all this. Here are some properties that you should remember. This properties is valid for inverse Fourier transform. Linearity, it holds, that is af1t plus bf2t is equal to af1 omega plus bf2 omega, right? Similarly, time shifting, whenever you are shifting in time, you have to multiply by exponential of minus j omega t in the frequency domain, right, and into the f of omega. Then frequency shifting, that is whenever you are multiplying it with the exponential of j omega t in time domain, then automatically it will shift in the frequency domain. Scaling, it will be divided by the f of omega. Time reversal, same time in the frequency reversal. Convolution, if you are taking convolution in time domain, it will be product, that is multiplication in the frequency domain. Multiplication, again it will be in the convolution, right? So these are the properties. Some more properties is continued. Duality properties is there. Parseval's theorem is also, that is time domain frequency domain, and integrate differentiation. Differentiation means whenever you are taking the differentiation in time domain, in frequency domain it will multiply by j omega and to the power n will be equal to the n, how many times you are differentiating the frequency, the function. Integration means f of omega divided by j omega. So here you have to the is plus, these things also will be there. So here it will be f of omega by j omega, right? So these are the properties. Here are some examples, like for the time shifting properties. So as per time shifting properties, if you are shifting in the time domain, multiplying the frequency domain by this amount. So for example, here is your exponential of minus t, you are they are multiplying by e to the power minus t in this function u of t. So we know that Fourier transform of u of t, that is just you can put 1 into it minus j omega t and you will get this function, right? And now suppose t naught is equal to 2, right? So you are shifting it by time, that is f of t minus 2. So technically here you have to multiply e to the power minus t by 2 and u of t minus 2. This is your original function. So the new function is this. Now if you will take the Fourier transform, you will get how much? F of omega e to the power minus j omega t. And same things you can get by using this property, right? How? Substitute f of omega by 1 of j omega directly here. So f, like f of omega, that is Fourier transform of this is already we know 1 by j omega, and here it will be equal to in the multiplication, that is e to the power minus j twice pi. So that's a direct way to find out the value of the Fourier transform using the property. Now another example for scaling, and for scaling, whenever you are multiplying with any constant number, then it will be 1 divided by a, that number, and f of omega by a. As for example, here you are multiplying by 2, so 1 over 1 plus omega square by 4, 2 into 4, 2 into 2, 2 into whole square, this is 4, right? So we'll get this number. Why is it so? Because f of 2 omega, that is f of 2 omega means, suppose f of t is e to the power minus t. So already we know that the Fourier transform of exponential function is nothing. This is the 1 divided by 1 plus omega square. So omega is your omega by 2, like that we can get the values. Similarly, f of 2t, you are getting e to the power minus 2t, you can get the integration, and using this property, if you put, you will get the same value, right? So first find out the Fourier transform using this exponential technique, using the normal, that is multiplication, using the e to the power minus j omega t, and in the second time you can use this the property, and you will get the value of the Fourier transform. If you'll check, both will be matched. Okay. Now, so these are the properties. Now let's talk about the the analysis of LTI. LTI is your linear time invariant continuous time signal, right? So how is it behave? So first of all, the Fourier transform of continuous time signals we can write like this. So xt is that the function in the time domain, and this is the factor that we are multiplying in order to convert into the frequency domain, right? So frequency response. So what is this frequency response? So frequency response h of omega characterizes how the system modifies the amplitudes and the phase of each frequency components of the input. So the frequency response will tell about the system, that how the system will behave with the inputs. So that is called the frequency response, right? So as for example, here is your frequency response of this particular filter. So 1 by RC to the power minus T by RC, this is a function for which you wanted to get the frequency response. So for RC circuit you can get, and so if you're converting into the time domain, so convert into the frequency domain, so this is in the time domain. And now further, if you will integrate this function, you will get the function that is h of j omega divided is equal to 1 by RC, and this function. So this is nothing, this is the frequency response of your RC circuit, right? So now if you have the frequency response, then it is very easy to get the output, because the transfer function, this is the frequency response, also called as the transfer function of this RC circuit. So once you will have the transfer function, then you can get the output y of t very easily for different inputs. So you can multiply that inputs ut or del t or whatever the xt you wanted to get, right? So correspondingly, if you have the frequency response of any system, then it is very easy to get the output for different inputs, right? So this is the one of the frequency response of the RC filter. Similarly, now we have the frequency response. So now it is very easy to get the impulse response. How can we get it? So in the frequency domain, simply you can multiply by the del of t, that is in the frequency domain, that is 1. And so you can convert back into the time domain, that is inverse function, inverse of the Fourier transform. Then you will get this value, right? So 1 by twice pi. And this is the frequency response h of j omega of that particular function, and multiply it to the power minus j omega t, right? So what is this h of t? H of t is your the h of t is the obtained from the frequency response using the inverse response. So this will give you the inverse impulse response of your that system. So this is your transfer function h of j omega, and input is your del t, suppose impulse response, so that is why del t, that is 1. So no need to multiply anything, and then this factor we are multiplying and getting back into the time, right? As for example, h of j omega, this is the transfer function that already we got. This is for the filter, RC filter, low pass filter. And so the impulse response, how your your filter will behave with the impulse function. So just multiply by 1 because del of t, and then I take the inverse. So if we'll take the inverse, it will be 1 by RC this function. So this is the actual output. So this will be the output of the impulse response of this low pass filter, right? So how to get? So in order to get the impulse response of any filter, first you should have the the response, the transfer function. So transfer function into the, you can multiply with the the inputs, whatever inputs you have. So for the time being we are considering impulse response, so 1, and then take back into the time domain from frequency domain. So that will be the results of impulse response. Similarly, if you want to get the step response, so in that case you have to multiply by ut. So yt will be what? Yt will be the h of t into u of t. So in the frequency domain, time domain, h of t into the convolution of this u of t. In the frequency domain, your yt will be h of omega into u of omega, right? So multiply your transfer function with the step function, and then get back into the time domain using the inverse Fourier transform. That will be the result of the unit step response of that particular function, right? So as for example here, for RC low pass filter, here h of omega is here. So this is the the transfer function or the frequency response of a RC low pass filter, and here is the step response, right? So this is the output step response. So first multiply, so this is the Fourier transform of the step function, and the Fourier the Fourier transform that is in the frequency domain, frequency domain of your function, that is the RC low pass filter. So multiply both and then take back into the time domain, means using the inverse Fourier transform. So results will be 1 minus e to the power minus t by RC. So this is the final unit step response of RC low pass filter, having the frequency response of 1 over 1 plus j omega RC, right? So in this manner, whatever, like for any response you can get, so only you should have the input. So replace this input here, and if you have the frequency response of that function, replace it there, and then multiply and convert back into the time domain, you will get the response, right? Response means here is unit response, and you will get the the output or the response for that particular input, right? So this is exactly way to get. Okay, so here is the final responses. So these are the transfer function for RC low pass filter, high pass filter, and underdamped RLC filter. And here is the impulse response. So these are the the outputs if you are giving the input as a impulse function, right? So just convert back into the frequency domain, that is inverse Fourier transform. So if you convert this function into the inverse Fourier transform, it will be this, for this here, this one, and likewise, right? So these are the final output of the impulse response for these low pass filter. Okay, so that's all in this session. Thank you to join, and now we'll come with another session for the particular unit second. Thank you to join.